Okay. Am I audible? Okay, we'll start the session. I hope I am audible and my screen is visible to everyone. So, welcome back to the 10th live session of Solar Energy Engineering and Technology. Myself, Soumya Tiwari. I'm PMR scholar at Department of Sustainable Energy Engineering, IIT Kanpur. And in this session, we'll mainly learn about concentrating solar power technology. So, till now, what we have seen is the flat plate collectors, right? We have also seen the solar air heater. Those were one of the two application of solar thermal applications. Now we are going to learn about the concentrating solar power technology. So what I'll do, I will just get brief of all the lectures, and then at last we'll solve some numericals as usual. Okay. So what is difference between the your flat plate collectors and this concentrating solar power technology? In flat plate collector, we were directly utilizing the incoming solar radiation that was falling on the flat plate, right? But in concentrating solar power technology, we are going to use some devices, maybe it might be mirror or lens, that will actually concentrate the incoming solar radiation onto a smaller receiver area, thereby increasing the concentration and increasing the flux received at those small area, and thereby increasing the temperature and efficiency of the concentrating solar power technology. So basically we utilize some mirror and lenses to concentrate sun's energy and convert it into a high temperature heat in a concentrating solar power technology. Now, if we talk about the component of a concentrating solar power technology, then we have a focusing device. So this focusing device could be anything. It could be a reflector, it could be a mirror, it could be a lens. The basic agenda of using this focusing device, it's used to concentrate the incoming solar radiation falling on this focusing device. Then at a receiver end, we have some absorber or receiver where our actual applications take place. So our heat absorption take place, right? And then we need a tracking device also. So in if you remember, in a flat plate collector, we don't need any tracking device, right? But in this concentrating solar power technology, we need some tracking devices which will actually track the movement of sun, such that at all the time the radiation falling on the receiver or from reflector will be basically received at the receiver. Okay. Now, so we have some solar concentrator advantages, like better thermodynamic efficiency, reduced losses, high storage heat storage capacity, and see, we can reach temperature as high as 3500 degrees Celsius. And basically this heat can be further also utilized to generate electricity. So we can use some steam generators, and then we can produce electricity. And this can be also used in PV technology also, right? Now, the drawback of solar concentrator are that we are only using the direct beams, right? The diffuse radiation cannot be, uh, diffuse radiation does not have any direction, right? So they cannot be basically concentrated. So only direct radiation has been utilized in concentrating solar power technology, and for its viable application, the clear sky is more preferred at any location. Now, so the functioning of solar technology. Okay, right. So basically, as I have told previously, that um, we have some lens or mirror used to concentrate the solar radiation onto a thermal receiver, and this receiver absorbs and converts sunlight into heat, and this heat can be further utilized to generate steam in a steam generator, and it can be further converted into electricity. Now the range is from few kilowatt to 200 to 350 megawatt, that can be in a remote power system, that can be utilized or generated by the solar concentrator. Now if you want to compare with the conventional resources, then 350 megawatt of electricity produced from this concentrating solar power is equivalent in energy to 2.3 million barrel of oil utilized to generate this energy, right? So you can see how much energy or how much fossil fuel we can conserve by utilizing this uh, solar concentrator. Now, in solar thermomechanical system, what we have is, as the name suggests, from solar we are generating the thermal energy, and this thermal energy is further used to generate the mechanical energy, right? So, in mechanical energy or in form of shaft power and like water lifting and all, and this mechanical energy can be further utilized to generate the electricity using your generator, right? So, it's called solar thermomechanical system. Now the efficiency of these solar thermomechanical system are very less because so many components are used, right? And as the collector temperature increases, the losses increases, the collector system efficiency decreases. But if we increase the working fluid temperature, then your efficiency of the heat engine in this solar thermomechanical system, that increases. Now, so if you see here, so we have this high temperature heat receiver in which your fluid is fed, right? So a thermal energy is absorbed by this fluid, is then basically fed to the steam generator, where steam is generated. Heat exchange take place between this fluid and the steam, and your steam is generated, and this steam is further utilized to drive the turbine, and we can further this mechanical energy can be further used to in generator to generate your electrical energy. So if you talk about the parameter, important parameter in solar concentrator, we need to know what is aperture area, what is absorber area, what is acceptance angle, what is intercept. So aperture area, say if this is your device, so uh, aperture area is the area through which your solar radiation is incident, right? And the absorber area is on which your basically the small area on which your this concentrated solar radiation that falls. So this is your receiver area or absorber area. So it is the area from which your q useful energy is utilized. Now acceptance angle is um, so the whatever um, solar radiation is going from your concentrated from the your concentrator, the whole of it does not use aperture area or your receiver area. A part of it is only intercepted, right? So the angular limit to which the incident ray may deviate from the normal to the aperture, so this deviation we are talking about, to the aperture plane and still reaches the absorber or receiver, that angle is known as acceptance angle. So I will say this area is your 2 theta, this is your acceptance angle. Now intercept, what is intercept? Intercept is basically after the reflection from the concentrator, um, the ratio of energy intercepted by the absorber of a given width to the total energy redirected by the focusing device. So all the reflected rays does not reach to the absorber, only a part of it is received at the absorber. So that ratio is known as intercept factor. Optical efficiency, we know that how much area is being absorbed by the absorber to the incident energy on the your concentrator aperture, right? So these are some important terms that will be used, that we need to have an understanding of. Now another is the concentration ratio. So concentration ratio is basically geometrical, or it can be defined in term of local concentration ratio. So geometrical, we are talking about it's a ratio of this aperture area to this absorber area. And if we would talk about the concentration in term of concentration ratio, it is the ratio of the solar radiation at any point on this absorber surface to the incident on the this aperture surface. Note that the half angle subtended by the sun at the earth is 0.267 degree. This value you need to remember. Okay. So so how this acceptance angle and concentration ratio are interrelated, or how it's affect. So if there will be larger acceptance angle, right? So less your seasonal adjustment needed to take place. If the aperture area is very small, right, then the your tracking requirement will be continuous, right? To ensure that whatever solar radiation are falling, the maximum should fall in this smaller acceptance angle range. Now this or I will not explain, I will just explain what is the important formula. So if we'll see, for a circular concentrator, this the maximum uh, your concentration ratio is given by 1 by sine square theta s, where theta is the angle subtended by sun onto the earth. And for linear concentrator, the maximum concentration is given by 1 by sine theta s. Okay, this formula you need to remember. Okay, so for theta is equal to 0.267, the maximum, that is the angle actually subtended by sun on the earth. The maximum possible concentration for circular concentration is 46,000, and then for linear is it's 215. Okay, so it's maximum. Now, okay, so this you need to remember. So a point focus system, sort of circular thing, right? So it's a maximum concentration will be sine 1 by sine square theta, and for line focusing system it will be 1 by sine theta. This you need to remember. Now, so the different classification of solar concentrator has been mentioned here. So let's just see the summarized uh, thing here. Okay, so depending on what mode of classification we are talking about, if we are talking about the based on the aperture type, so the basically your concentrating uh, component could be a refracting type or reflecting type. So example of refracting type is the Fresnel lens, and the reflecting type is your utilizing the mirror. So this reflecting type surface may be a parabolic, spherical, or flat, depending on what application we are going for. If we're classifying based on the image formation, then it could be where the at the concentration point at the receiver and the image is not forming, so it's a non-imaging type. If we are talking about the imaging type, then it could be a line focus type or a point focus type. So the line focus is also known as 2D, and the point focus is also known as 3D. If we're talking about the operating temperature, then we have low, medium, and high, depending on which type of concentrator we are going to use. And based on tracking mechanism, it could be a single tracking or two-axis tracking. Okay, so here it's the four main important concentrating solar technology are mentioned here: parabolic trough, disk Stirling, center Dawn, or Fresnel lens. So each have their advantages and disadvantages, and the storage integration possibility that has mentioned here. Um, so depending on so you can go back to the lecture, and you can see this theoretical point. What I want to mention is, okay, the thermal analysis of the concentrator system. We know this equation. We have seen this equation again and again. Q is full equal to your whatever your solar beam radiation is there on your effective aperture area. This is your incoming solar flux, right? On a particular area minus your loss. Your loss will be your overall loss coefficient, heat loss coefficient, into your area of absorber surface, right? This is area of absorber surface minus your average temperature of the absorber surface minus your ambient temperature. This formula we have seen again and again. It's just the energy balance equation. Now, uh, based on this, we can calculate your Q useful, right? And we already know that the concentration ratio is area of aperture upon area of your receiver. Now, um, this graph basically shows as the receiver temperature increases, what is the system efficiency. Note that the system efficiency is not just the your collector efficiency, it's your function of both collector efficiency and your mechanical efficiency. So we can see that at the receiver temperature increases, how the system efficiency uh, increases and then decreases depending on what concentration ratio we are talking about. Okay, so right, so the overall efficiency of a concentrating solar your uh, uh, application is the whole system efficiency is the multiplication of your collector efficiency and then Carnot efficiency. So with increasing the temperature, this collector temperature will rise, so more heat losses will be there to the surrounding. So this efficiency decreases, and as the temperature increases at the outlet, your Carnot efficiency increases, right? So that is the effect of temperature on these two factors, basically these two efficiency, and this you need to remember. You also need to remember the range of these, how much you should have awareness about what is the concentration ratio of the typical this four concentrating basically devices, and what temperature we can reach. Okay, so we'll just skip this, the application part. Okay, this table is important. You need to remember the operating temperature, the concentration ratio. You need to have some idea about uh, what is the operating temperature and what is the your concentration ratio. The parabolic trough collector has say the uh, lowest operating temperature, some 220 to 400 degrees Celsius, and concentration ratio of 15 to 45. The solar power tower has high concentration ratio 150 to 1500, and thereby leading to the operating temperature of 300 to 565 degrees Celsius. The linear Fresnel reflector have much less, I think least 20, 10 to 50 concentration ratio. Thereby the temperature, the operating temperature is also less here, so 50 to 300. And then we have a parabolic disk. For that, concentration ratio is as high as 1000, and the temperature maximum can be reached here at around 1500. So this table is important. You need to have idea about um, the temperature and the concentration ratio. Now, analysis of parabolic trough collectors. I will not go into the detail. I'll just summarize what are the important parameters and the formula that you need to remember. Okay. So you as you see can you can see that this is your parabolic trough collector, right? And basically the incoming solar radiation are being concentrated onto a linear this absorber tube along the line. That's why it's called linear or 2D type of concentration concentrator. Okay, so it's the concentration is along a line. Now assuming some assumption and think the what is important is the concentration ratio. So as we know that the concentration ratio is your aperture area upon the your receiver area. So your effective aperture area is basically, if this is the width and this is the d naught diameter of this tube, it will be w minus d naught into l upon your absorber area will be pi d naught into L, if d naught is the diameter of this outer diameter of this absorber tube. Now we will do the basic energy balance, where we will note that here we are basically considering both the thing, the beam radiation absorbed in the absorber tube after reflection from this parabolic trough collector, and also the direct beam radiation falling onto this absorber tube. Okay, so the absorber incident beam radiation which fall directly on the absorber tube, plus your the reflected radiation falling on this absorber tube after reflection from this parabolic trough. And this will be your utilized, actually utilized will be minus your loss, right? So if you rearrange and solve and whatever, so your main important parameter of concentrating collector is this collector efficiency, right? Then we have the temperature distribution, how does it take place. Then we have this useful heat gain, right? That will be asked in the question, what will be the useful heat gain for a given type of concentrating solar device, right? Then we have this heat removal factor. This factor we have already seen again and again in the flat plate collector and also in solar air heater. So I hope that by now these terms are already clear. Just the formula changes because the in linear flat plate collector, or sorry, in a flat plate collector the concentration ratio was 1, right? But in this solar concentrating device, now concentration ratio are going to be have some values. So that factor has been just adjusted in this formulas and this factors. So you need so the structure of the formula is same, it's very easy to remember. So that's why I'm telling these are the important formula that you need to remember: the useful heat gain and your collector heat remover efficiency, then your instantaneous collection efficiency, it will be q utilized upon your incident whatever is on the your basically your input, right? So it will be ib into rb plus id into rd. B is for beam, d is for diffuse, and sorry, this d will be the ground reflected radiation. That if that will be neglected, then it will be ibrb into your area width into length of your uh, collector, right? So this is the formula. So these are the important formula you need to remember, because numerical will be framed on this question only. We already know this rb value, right? For beam radiation it's cos theta upon cos theta z. Theta is for the uh, basically at a slope of beta, right? And theta z is for the horizontal. This thing we have already learned, right? Now if you want to calculate the overall loss coefficient and the heat transfer correlation, if you need to basically see, if you need to calculate in the question, then these are the important formula that you need to remember: this formula and this correlation. Okay, these are the important correlation that we need to remember. I hope we are already aware about how this from Nusselt number, how this heat transfer coefficient Nusselt number is equal to HL by K, and from there we basically calculate the value of H heat transfer coefficient, and the correlation for the same is given mentioned here. Okay, so these things you need to remember. Now, this was for the heat transfer coefficient between the absorber tube and the cover. So we have the absorber tube and a cover, right? Cover, and this is your absorber tube, right? So this is the heat transfer coefficient for was for this, right? Now we are talking about heat transfer coefficient on the inside of the absorber tube. So now we are, if you want to calculate the heat transfer coefficient inside of this absorber tube, then for that we already know that the uh, for laminar flow and turbulent flow the Nusselt number value. This is note that this is for fully developed flow, and we have the Dittus-Boelter equation to calculate the Nusselt number, and then from there we can calculate the heat transfer coefficient, right? It will be HL by K equal to. And if we want to calculate the pressure drop, we already know the friction factor, how to calculate, right? And then from there we can calculate the pressure drop, that will be HFLV square by 2E. This also we have already seen in the um, your air heater, right? Now I will skip this theoretical part. We have so many questions to solve, so I will not go into the details. This theoretical part you can go by yourself. Um, okay, now coming to this central power receiver system. In central power receiver system, what we have is we have a solar tower, right? This is the tower at the top of which your receiver is placed, and here we have a basically mirror reflector, right? Heliostat. So whatever radiation is falling on this mirror is been reflected by this mirror, and then they get concentrated onto this receiver. And if you do the analysis of the central power system, basically receiver system, then we have um, okay, so the formula here given here are, I think, not very visible to you. Okay, but just let me summarize here. So basically, okay, so whatever area of the mirror, n is the number of mirror heliostat, and am is your area of those mirror, that will be equal to your phi into ag. What is ag? Is your area of the ground, and phi is the fraction of the ground that has been covered by this mirror. So this basically equation comes from that understanding. Now if you do the energy balance and all, your q utilized will be, is my screen visible to you all? Is my screen visible to you all? Okay. Oh, it's fine now, right? Okay, so concentration ratio in case of solar tower will be your aperture area upon your receiver area, right? So it will be your aperture area is basically your number of heliostat into area of those heliostat, or it could be replaced by sine to ag, right? This will be your concentration ratio. This you need to remember, and depending on whether your mirror is circular or this this basically the size of image at the absorber form, this is the formula for this is given here, where h is the height of the tower, cos phi s is your angle subtended by sun at the earth, right? This, and theta e is your angular error. Okay, so this formula you need to remember. Area of the absorber, this formula also you need to remember. What will be the area of absorber, and the concentration ratio, obviously if you know the area of your heliostat total area, and then area of your absorber, you can already calculate the concentration ratio. Now this is the numerical based on the solar tower. So say that in a central receiver collector, the height of the tower is given 180 meter. So the height of the tower is given 150 meter, and the rim angle is given your, basically phi r is given 50 degree, and diameter of the mirror is also given. So the diameter of mirror is given 4.5 meter. Okay, now find the size of the image formed by the outermost mirror at the receiver. So we have been asked about the size of the image, area of the absorber, and then concentration ratio. Assuming that in the first case the mirror are the flat mirror, and the in second case the mirror are the disk mirror. Okay, what else is given? Your a fraction of area, fraction of the ground covered by the mirror is given, and your theta is given. This is the angular error, right? In radian it's given. We already know that the theta s, angle subtended by sun onto the earth, is 0.53 degree, right? This value you need to remember. Now we all also know that how to convert degree into radian, right? So we will so let's see. So we already need know the formula for the size of the image, the area of the absorber, and the concentration ratio. This formula. That's why I have said that this formula you need to remember. Okay. So let's see it one by one. Okay. So the for flat mirror, uh, your let's see all the values here. Your h is given. H is 150 meter, right? Phi r is given here. Basically, rim is given your 50 degree, right? Your theta e is given 0.02. This is in radian. Your theta s is already given. This is given 0.53. This is in degree, right? Uh, note that it should be converted in radian also while putting the value here, right? And then we already know the diameter of the mirror w, right? That is given 4.5 meter. We know all the values we can put into the equation, and we can calculate the basically length of the image formed. We can calculate the your receiver area, and then from there we can calculate the concentration ratio. Similarly, for the disk mirror, we exclude this value, and then the formula is same for the rest of the thing, and we can see that in the flat mirror your concentration ratio is 330, but if you use the disk mirror, the concentration ratio has increased to 2412. So we can see which mirror is will be required for higher concentration value, the disk mirror, right? Okay, I will also not go in detail in these theoretical questions, basically theoretical part. What I will do is, let's skip this all and go straight back to the numerical problem. Okay, this is the another numerical. So what has been asked is calculate the heat removal factor, the FR. Okay, sorry for the right. So what has been given in the question is calculate the heat removal factor FR, the useful heat gain QU, and the exit fluid temperature, the TF naught. And also has been asked the collection efficiency, right? For a cylindrical parabolic concentrator having a 3 meter width, 10 meter length, and the outside diameter of the absorber tube being 7 centimeter. The date is also given, the 15th April. The time is also given, 12:30. Consider the latitude and slope. So your phi latitude and the slope beta is also given. The temperature of the fluid to be heated at the inlet. The fluid inlet temperature is given, TFI, and the flow rate is also given in kg per hour. The incident beam radiation is 750 watt per meter square. The ambient temperature is 27 degrees Celsius. The optical properties are given. This rho is your spectral reflectivity. So if you talk about, so this is your reflector, cylindrical parabolic concentrator. Okay. So this value is given 750 watt per meter square. The spectral reflectivity of this surface is also given, 0.85. The transmittivity and absorptivity for beam radiation uh, through this cover is also given, 0.78. The intercept factor is also given, 0.93. The Cp of water is given, um, and then your collector efficiency factor is already given in the question, F dash, with the heat loss coefficient. Now let's see what else we can get from this questions. So we have already given the date, right? 15th April. We can calculate the days from the 1 January, that will be 105, and we can calculate the declination angle for this particular day, right? The beta is already given in the question. The phi is already given in the question. What else, the angles we want to know? We omega, the hour angle. So it's given 12:30. 12:30 will be corresponding to half of the 15 degree. 1 hour correspond to 15 degree, if you remember. Then half hour from the solar noon will be correspond to 15 by 2, 7.5 degree, and since it's afternoon, then the sign will be negative, right? Now, the absorber solar flux that has been received at the absorber, that how that will be calculated? What has been reflected plus what has been directly incident on this absorber, the sum of these two values. Now if you'll see how this has been mentioned, then whatever beam radiation is falling on the this reflector, not all of it has been reflected. So a part of it has been reflected. So if you'll see, if this is IB to RB, whatever has been incident beam radiation incident on this reflector, spectral reflectivity will be multiplied to account for this factor. Now, whatever beam radiation has been basically reflected from this concentrator, not all has been received onto this absorber, right? So intercept factor we are considering for that thing, we are including this intercept factor. Now, whatever has been received on this absorber tube, a part of it has only basically goes to your from cover to this your absorber tube. So for that we include your transmittivity absorptivity factor for beam radiation. I hope it's clear how this basically whole terms comes into picture. And this is for the direct beam. So basically this, if you, we are talking about solar flux, this if you multiply it by W by D naught, then we can get the whole energy value, right? So this is the absorbed solar flux equation. You can remember it, or you can understand how this equation is written. Now for that, what we already know, rho, we already know intercept, we know tau alpha value for beam radiation, we know the outer diameter of the this absorber tube, we know the width, we know the IB value. What we don't know is this RB value, right, for beam radiation. For that we have already seen again and again, it will be cos theta upon cos theta z, which is the function of your all the angular declination angle, your slope, your omega hour angle, and your latitude angle. Okay, so you can calculate this RB value. Now after calculating this RB value, we can calculate the solar flux incident on this uh, your cover, or your absorber tube, to say it clearly. Now, for heat removal factor, if you want to calculate the Q useful, for that you need to know the heat removal factor, right? In term of calculating what is the useful heat gain. So, for heat removal factor, we already know this formula, right? So it's m dot Cp upon pi d naught L into overall heat loss coefficient into 1 minus e to power minus f dash pi d naught UL, your overall heat loss coefficient into L dash upon m dot Cp. So f dash is already given in the question. What we don't know is this term, right? This will be used again and again here. So this is reciprocal of whatever has been mentioned here. So let's see each of the term. Mass flow rate is given in kg per hour. You need to change it in kg per second. Now we can calculate this factor. Cp value already given in the question, and rest of the value we already know. We can calculate this term, and finally you can calculate the Fr value. Knowing the Fr value, heat removal factor, you can calculate a useful heat gain in term of fluid inlet temperature. If you remember, by using Fr, you can use the calculate the Q in term of TFI, and note that here now concentration ratio comes into picture. In flat plate collector, this C was not coming into the formula. Now to calculate the concentration ratio, we already know that what is the concentration ratio. It's effective aperture area upon your absorber area, right? So it will be W minus D naught. So if this is your concentrator and this is your absorber tube, and this is your width W, and this is your D naught, so it will be W minus D naught into this length, right? Upon your absorber area will be pi d naught into L. So from here you can see the concentration ratio is coming to be 13.32. Knowing all this value, you can calculate the Q useful value. If you have known the Q useful value, this much amount of energy is actually utilized to heat the fluid. So it will be equal to m dot Cp, the fluid temperature at outlet, upon minus fluid temperature at inlet. From there you can calculate the Tf naught, and then you can calculate the instantaneous efficiency, which will be equal to your output upon input. Your output is your heat utilized, upon input is your whatever flux we are receiving. So it will be Ib into Rb into your area, which will be W into L, right? So you can calculate instantaneous efficiency, which will come to be 43.35%. So this is all the important parameter that you need to calculate while designing a concentrating solar concentrating devices. Okay. Now I hope this question was clear. Any doubt in this question? Okay. Now let's solve some questions. Okay. I hope the question is clearly visible. So I will read aloud the question. So for a linear concentrator with an acceptance angle of 15 degree, what will be the concentration ratio of the system? So for a linear, okay, Okay, we have got one answer, option D. Okay, let's see the solution for this question. So, for a linear line focus concentrator with an acceptance angle of 15 degree, what is the concentration ratio of the system? So, we already know that the, say, scissor, and then this is your aperture, and then this is your receiver. Okay, this is your area of aperture, and this is your area of receiver. This distance is r, and what else? The acceptance angle. Okay, now, so the in question what has been given is your acceptance angle. So your acceptance angle will be 2 theta. It's given 15 degree, right? Now we already know that for linear system, for linear or line focused concentrator, your your concentration ratio is given as your area of aperture upon area of receiver, which is equal to 1 by, this is sine theta, right? If you remember this formula, right? So it's for 2D system. Linear can be also known as the 2D system, right? So if we'll solve this, it will be 1 by sine theta will be sine. Now your theta will be 15 by 2. Okay, so it will be 7.5 degree. Okay, so it will be sine 7.5 degree, which will be your, if we'll solve this, it will be 7 point, I think it will come 7.66. Okay, so that will be your answer. So the correct answer will be option B. Okay, now the next question is, which of the following collector has maximum concentration ratio? Is it a central tower receiver, or paraboloidal concentrator, or cylindrical parabolic concentrator, or Fresnel concentrator? Okay, let's see the solution for this question. So that's why I reminded you all that we need to know which type of solar concentrator is used for, um, uh, um, basically which application, depending on what is their concentration ratio and their operating temperature, that you need to have awareness of. So the maximum concentration ratio is for the central tower. Okay, so if you remember, um, your central tower, I think The values were for parabolic dish. Uh, the parabolic dish was, I think it was around, concentration ratio was around 200, and then for solar tower it was around, um, I think it was around 500, right? So okay, so for uh, the central tower receiver has maximum concentration ratio. The fractional concentrator have the least concentration ratio, if I remember. For linear fractional concentration, it was around 10 to 40, if I remember. Okay, correctly. And then you have your parabolic concentrator, then we have parabolite concentrator, and then we have our central tower receiver. Now, this is the next question. What will be the collector efficiency of a solar concentrating power plant? Uh, the collector efficiency of a solar concentrating power plant is 28% and the mechanical efficiency is 90%. What is the overall efficiency of this concentrating solar plant, power plant? Okay, we have got one answer, which is option D. Let's see this question also. So what's given in the question is your collector efficiency is given, right? Collector efficiency is given, which is 28%, and your Carnot efficiency or mechanical efficiency is given 90%. We already know that the your overall system efficiency is, for a thermomechanical plant, it will be your collector efficiency into your mechanical efficiency, right? Which will be equal to your, if you multiply these two, it will be 0.28 into your zero point 0.9, right? Which will come to be, if you multiply, if you are going for the percentage thing, then it will come to be your 25.2%. So the correct option will be option D only. Okay, so the next question is, match the following concentrating collector with their output temperature range. So we have parabolic tuff collector, the solar power tower, the linear reflector, and your parabolite dish. Okay, we got option. One of the answer is option A. Okay, let's see. So So the what we know is the for parabolic trough collector, uh, this option will be there. So let's see the answer. So it's option A only. So for parabolic trough collector, if we'll see your uh, concentration ratio was around 15 to 45, right? And then for solar power tower we have higher temperature, operating temperature, or the output temperature. And in linear Fresnel lens we have less, and then your parabolic dish has also very high temperature. So if we'll match this, then your parabolic trough collector temperature range is from 20 to 400 degrees Celsius. Solar power tower have very high temperature range, so it's 300 to 565 degrees Celsius. Your Fresnel uh, reflector have low temperature range, and then parabolic dish is a high temperature application, right? So it's 130 to 1500 degrees Celsius. So option A is correct. Now this is the question. For a collector having an aperture area of 240 meter square, concentration ratio of 20, the absorber surface achieve a temperature of 375 degrees Celsius, and the overall heat loss coefficient is 5 watt per meter square per degree Celsius. Ambient air temperature is given 25 degrees Celsius. Solar beam radiation falling on the absorber is given. Now what has been asked is what is the rate of heat loss from the absorber. And further you can also calculate the rate of heat utilized, right? So what is the heat lost in a given system with a given parameter, and what is the heat utilized? Well, let's see this question also. So what's given in the question is, okay, for a collector having an aperture area of aperture is given 240 meter square. Okay, the concentration ratio is given 20. The absorber area achieve a temperature of 375 degrees. So if this is your absorber, right? So its temperature is given. So let's mention this by R. So 375 degree. Now the overall heat loss coefficient is given. So your UL is given 650. This is no, sorry, this is 5. So don't know, it's not taking, but okay. So it's given 5. This is watt per meter square per degree Celsius, and the ambient air is given. This is 25 degrees Celsius. Now the solar beam flux falling on this aperture area is given. IB is given 650 watt per meter square. Now we have been asked the rate of heat loss. We have been asked what is the rate of heat loss in watt, kilowatt. Okay, it's asked in kilowatt, and the rate of useful heat gain. So Q has been asked in kilowatt. So let's see how to solve this question. So okay, again writing the values that we have seen. So area of aperture was given 240 meter square. Then your concentration ratio was 20, and your absorber, your mean temperature was given 375 degrees Celsius. Overall heat loss coefficient was given 5 watt per meter square per degree Celsius. Ambient temperature was 25 degrees Celsius, and your beam radiation was 650 watt per meter square. Now to calculate the rate of heat loss, so rate of heat loss, the QL, that will be equal to your overall heat loss coefficient, right, into your area of your receiver, right, or absorber you can say, into your, what is the area of your receiver or absorber, that is already given in the question, minus your ambient temperature. Basically it will be that only. You know the area of aperture, what will be your area of receiver or area of absorber. So the notation might be different, so let's say it by P, AR or AP. Okay, that will be equal to your area of aperture upon concentration ratio. So if you remember your concentration ratio was area of aperture upon area of receiver, right? So this was your formula. So from there, if you want to calculate the area of your receiver or absorber, it will be area of aperture upon your concentration ratio. That will come to be 240 meter square upon your concentration ratio is 20. So this will come to be 12 meter square, right? So your QL will be, it will be UL. What is UL is 5 into area of receiver is 12 into what is mean absorber temperature, it's 375 minus ambient is 25, right? So it will be 5 into 12 into this will be 350, right? And this will come to be 21,000 watt, or you can write it as 21 kilowatt. Okay, so that will be your QL. Now what will be Q useful? we already know the heat loss. So from here we can already calculate the useful. It will be whatever has been incident on the basically your absorber, right? IB into your area of your basically your aperture, right? Minus your Q lost, right? So you know already know the value of IB. It's 650 watt per meter square into your area of aperture will be your 240 meter square minus Q lost is your so this will be in watt. So here also we'll keep the value, or let's say divide by 1000, then this will be your kilowatt, right? This will come in kilowatt minus 21. This is also in kilowatt. So if we'll solve this, so this will be okay. So it will be 156 minus 21. This will be in kilowatt, which will come to be U useful equal to this will be 135. Okay. So these are this is how we solve the question. So the correct answer is as you can see the 21 kilowatt and 135. So the 21 kilowatt and 135 are the correct answer. Hope this question is clear. Okay, let's move on to the next question. I will read aloud the question. So okay, the question is for a cylindrical parabolic concentrator. Okay, we have a cylindrical parabolic concentrator having 12-meter length, 3.5 meter width, and the inside and outside diameter of the absorber tube was 6 centimeter and 8 centimeter respectively. Now, the inlet temperature of the fluid to be heated is 150 degrees Celsius with the flow rate of 500 kg per hour. The incident beam radiation is 800 watt per meter square. Ambient temperature is 27 degrees Celsius. The heat transfer coefficient on the inside surface of the tube, that is given 50 watt per meter square per degree Celsius. Consider the latitude of the location and the slope 18.52 degree and 9.6 degree respectively. The optical properties are also given. The spectral reflectivity of the concentrator 0.85, average transmittivity absorptivity product for beam radiation 0.81, intercept factor is 0.93, specific heat 1.256 kilojoule per kg degree Celsius, overall heat loss coefficient 7.5, and the data was obtained for March 15th, 13-hour local apparent time. Now, what will be the useful heat gain in kilowatt? That we have to calculate. And from there we can also, okay, next we can also calculate the, so what will be Q useful? The outlet temperature of the fluid, T F naught, and the instantaneous collection efficiency. These three things we need to find out. So I'll give you a few minutes to solve this question and then I'll explain this question in detail. Okay, let's start solving this question. Um, so what's given in the question is a cylindrical parabolic concentrator is there. Okay. So okay, now what's given is it has 12-meter length. So this length is given 12-meter. Okay, 12-meter length is width is given. This is 3.5 meter. Okay, and the inside and outside diameter of the absorber tube. So for this absorber tube, this we have the absorber tube in which your fluid is flowing. This absorber tube. Okay, so what's given is the inside and outside diameter is given. So outside diameter is your uh, 8 centimeter and inside diameter is 6 centimeter. The inlet temperature of the fluid. So here the fluid inlet temperature is given. That is given your 150 degrees Celsius. Okay, and the mass flow rate is given. So the mass flow rate is given in 500 kg per hour. It's given in 500 kg per hour. Now the incident beam radiation is, so your incident beam radiation is given. This is given to be 800 watt per meter square. Okay, and the ambient air temperature is given. This is 27 degrees Celsius. The heat transfer coefficient on the inside surface of the tube. So here the heat transfer coefficient, here it's given 550 watt per meter square per degree Celsius. Consider the latitude of the location. So latitude is given your 18.52 degree. Your slope is given 9.6 degree. What else is given here is, so okay, let's start here. So what's angle has been mentioned here is your phi is given 18.52 degree. Your beta is given, slope was given 9.6 degree. Your spectral reflectivity was given 0.85. Your transmittivity absorptivity product for beam radiation, that was given to be average transmittivity absorptive product was 0.81. Okay, so this was 0.81 and your intercept factor was given 0.93. Cp is given 1.256 kilojoule per kg per degree Celsius. Overall heat loss coefficient is given 7.5. Okay, overall heat loss coefficient is given 7.5 watt per meter square per degree Celsius. The date is given 15th of March. Okay, so 15th of March will be, n value will be 31 plus 28 plus 15. This will come to be 74. So for n equal to 74, you can calculate the declination angle, right? So it will be 23.45 sine. This will be 360 by 365 into 284 plus n, right? So if we'll put the value of n74, it will come to be 23.45 into minus 0.1202. So this will come to be, okay, so the declination angle will be your minus 2.82 degree. Okay, so we know the declination angle, we know the phi, we know the beta, and what else is given in the question is omega for 13 hour. So for omega for 13 hour from solar noon, it will be 15 degree and it's afternoon, that's why the sign will be negative. Okay, So these four angles we have calculated. Now the first thing that we have been asked is the useful heat gain, right? Q useful. So for that, what we need to know is your whatever flux is falling on your absorber, right? Whatever flux is falling on your, after reflection, whatever is falling on your absorber tube, right? This S value. And to calculate the S value, we know the formula. S equal to, so this is IB into RB, right? For beam radiation. Then we have your whatever reflectivity is there for the your concentrator, then the intercept factor. So not all of it is reaching to the absorber tube. A part of only the a part of reflected radiation is only reaching to the absorber tube. For that we have the intercept factor. Then we have your cover. From for that we have your transmittive absorptive product for the beam radiation, right? And this is for your direct radiation falling on the absorber tube. So this will be IB into RB into your tau alpha for beam radiation, and then we have your D naught upon W minus D naught. Okay. So now we know reflectivity, you know intercept factor, we know tau alpha, you know IB, we know D naught W, D naught. What we don't know is this RB. So for RB, we already know this factor. It will be cos theta upon cos theta j, right? For horizontal and for uh, slope of beta angle. So this will be your, if you remember the formula, if it will be sine delta, sine phi minus beta plus cos delta, cos omega, cos phi minus beta divided by, this will be sine delta, sine phi for horizontal surface, and this will be cos delta, cos omega, and this will be cos phi. So if we put the value, so this will be sine delta is your declination angle is your minus 2.82 degree, right? So this will be sine phi is your 18.52, so it will be 18.52 minus your beta is 9.6 degree, right? Plus your cos delta is your minus 2.82, cos omega is minus 15, and cos phi minus beta is, your phi is 18.52 minus beta is 9.6, right? Divided by, we put the value, sine delta is minus 2.82, sine phi is 18.52 plus cos delta is minus 2.82, cos omega is minus 15, and cos phi is your 18.52. If you solve this, your RB will come to be 1.0515. Okay. So this will be your RB value. Now, from RB value, what we can calculate is, we now know all the values. We can put back into this equation, RB back into this equation, and put all the value of, so let's write it here only. So S equal to, this will be IB is your incident beam radiation was 800, right? 800 into your RB is 1.0515 into your reflectivity is point spectral reflectivity is 0.85 into intercept factor is your 0.93, and tau alpha average is 0.81. Okay, plus 800 into 1.0515 into 0.81, right? Tau alpha b, and this will be D naught is your outer diameter was 8 centimeter, right? So it will be 0.08 meter upon W minus D. Your width was 3.5 and your D is 0.08. If you solve this, your S value will be, it will come to be 554.563 watt per meter square. So this will be your flux that is actually receiving to your absorber. Now, what is the concentration ratio? This is your effective aperture area upon your absorber tube area, right? So this will be uh, W minus D naught into L upon pi D naught L, right? So it will be your W minus D naught upon pi D naught. I'll put the value, it will be 3.5 minus 0.08 divided by pi into 0.08. If it solve this, it will be 3.42 upon 0.2513. This will come to be 13.608. This is your concentration ratio. Now, uh, what will be your heat removal factor, right? For that, know the formula. It will be m dot cp pi d naught L into overall heat loss coefficient into 1 minus e to power minus of f dash upon this factor m dot cp. This will be pi d naught L into ul. Okay, so this is the formula for fr. We don't know the f dash value. Okay, collector heat removal factor. So for this we know the formula. It's ul upon 1 by ul plus d naught upon this is inner diameter into your heat transfer coefficient. So this value we know. Overall heat loss coefficient was 7.5. This will be 7.5 plus d naught we already know 0.08. D was 6 centimeter, right? So 0.06 into heat transfer coefficient was, sorry, it was your heat transfer coefficient was 50, right? So you'll multiply it by 50. If you solve this, your f dash value will come to be 0.833. Okay, now we'll put back into this equation. So fr will be now, okay, let's calculate this m dot cp also. Okay, so this factor m dot cp upon pi d naught L into ul, it will be your mass flow rate was 500 kg per hour. So remember to convert it into kg per second. Okay, into your cp was 1.256. uh, this was in kilojoule, right? So convert it into joule per kg per degree celsius, divided by, will be pi d naught is equal to 0.08. L is your length, that was 12 meter, and your ul is 7.5, right? Watt per meter square per degree celsius. So this value will come to be, I think this will be 7.71194. Okay, so this also you'll put in this equation to calculate the fr. So your fr will be basically, this will be 7.71194 into 1 minus e to power minus this f dash is 0.833 divided by this 7.71194. So your fr will be, if we'll solve this value will be, I think this value will be 0.7896. Okay, so you know the value of fr, you know this concentration ratio. What you can calculate from here is, okay, now q useful, you already know the formula for q useful in term of fr and inlet fluid temperature, right? So you q useful you can write as your fr, okay, into w minus d naught into l into your s minus overall heat loss coefficient upon concentration ratio into fluid inlet temperature and minus your ambient temperature. So in term of fr and fluid inlet temperature, you can write q useful um, as the shown formula. Okay, so from here you can calculate the, we know now all the value, right? So you know the fr value is basically your 0.7896, right? So Okay, so it's 0.7896 into W is your point 0. Okay, so this was width, so 3.5. Okay, minus D naught is your 0.08, L is your 12, right? Into S was your, okay, S was your 554.563. So it was 554.563 minus 7.5 upon concentration ratio was 13.608. Okay, and your fluid inlet temperature was 150, ambient was 27. So if you'll solve this, your Q useful will come to be, I think this will be 15.777 in kilowatt. Okay, now we know the Q useful. What else we can calculate from you? This is heat is actually utilized to heat the fluid, right? So Q useful, what we can write it as your mcp delta T, right? So delta T is your fluid outlet temperature minus fluid inlet temperature. If we write Q useful is 15.77, right? It's in kilowatt, so let's write in watt. Mass flow rate we already know. It was 500 kg per hour. Okay, so 500 by 3600 will be kg per second, right? Cp we already know 1.256 into 10 to power 3. This will be in joule per kg per degree Celsius. Uh, TF naught we need to calculate, and inlet fluid temperature was 150. So if we'll solve this, then your TF naught outlet temperature will be 90.40127 plus 150, which will come to be 240.40 degrees Celsius. So fluid outlet temperature will be 240.40 degrees Celsius. Okay. Now what else we can calculate from here is your instantaneous efficiency, right? So that will be your Q useful upon your whatever input was there. So it was IB into RB into your area. Area is your W into L, right? Width into length. So Q useful we already know, it's 15.77. In watt it will be 10 to power 3. This will be in watt upon IB is your 800. RB we have calculated. RB was 1.0515. Okay, IB was 1.0515. W was 3.5 and length was 12. Right? We'll solve this. Instantaneous efficiency will be, so this will be 15770 upon, if we'll multiply all this, this will be 35330.4. We are talking about percentage into 100, so this will come to be 44.65%. Okay, so these three was what was asked in the question. So the correct option will be, we have already calculated 15.77 as a useful heat gain. Outlet temperature was, I think it was 240.40, right? So it was 240, and instantaneous collection efficiency was 44.65. So this will be the answers. I hope this question is clear. How to solve this question? Okay, I have one last question. Okay, uh, let's see this question. So it's a question based on a solar tower. So a central receiver collector system consists of 1800 heliostats, each of 6.5 meter cross 6.5 meter in size. The height of the central tower is given. Okay, so the height of the central tower is given 84 meter. Okay, and the rim angle is given 81 degree. Assume that the angular error associated with the heliostat does not exceed 0.0055 radian and the heliostat are suitably dished. Okay, what will be the size of image formed by the outermost arc of the heliostat at the receiver? What will be the your aperture area, and what will be say your concentration ratio? These three we need to calculate. Okay, so since we have only 7 minutes left, I'll start solving this question along with you only. Okay, and let's see how to solve this question. Okay. Okay, what's given in the question was a solar tower is there. Okay, this is where your concentration occur, uh, and it's surrounded by several heliostats. Okay. Okay, so the number of heliostat was, so the number of heliostat was 1800. Each of area was 5.6, 6.5. So it was 6.5 cross 6.5. Okay, so each of the mirror has area 6.5 cross 6.5 meter square. The height was 84 meter. This height was 84 meter. Okay, what else was given? The rim angle was given. Okay, rim angle was 81 degree and the error is given 0.0055. This was given in radian. Okay, what else has been mentioned is it's dished. Okay, that you need to pay attention to while reading the question. Now what else we know is the angle subtended by sun onto the earth. That value we already know, which is 0.53. This is in degree. If you write it in radian, then it will be 0.53 into your pi by 180, right? So this will come to be 0.00931 in radian. Okay, now this is all given in the question. What we need to calculate is the size of image at the absorber if the mirror are suitably dished. Uh, so what will be the size of image at the absorber formed by the outermost arc of the heliostat? Okay, so for that we already know the formula for the dished one. Okay, length of the image. If you remember the formula, it was height upon, this is cos theta r, your rim angle, into your theta s, angle subtended by sun onto the earth, plus theta e. This one was for the dished one. Okay, so we put the values. H is 84, cos phi r is equal to phi r is 81 degree, right? Note that theta is given in the radian, theta e. So you will put the theta s value in radian only, not in degree, right? So it will be your 0.00931 plus this will be 0.0055. This is in radian, right? So if you solve this, your length of the image will be, this will be I think this will come out to be 7.952. This will be in meter. Okay, now what has been asked is the size of the receiver or the absorber. Size of the receiver. we already know the formula for this is pi by 2 this li square into 1 plus sine phi r rim angle minus cos phi r by 2. Okay, so if put the value, it will be pi by 2 into 7.952 square into 1 plus this will be sine phi r is 81, right, minus cos 81 degree divided by 2. I will solve this. This will be pi by 2 into 7.952 square into this will be 1.90947, or it will be 189.66 meter square. Okay. Now we know the area of the receiver, we know the length of the image. If we have been asked to calculate the concentration ratio, okay, so the concentration ratio, so the concentration ratio, okay, so the concentration ratio will be your area of your absorber. So your absorber area will be say, if you are using, if you remember the formula, it will be phi pi h square tan square phi r upon your receiver area is your AP, right, that we have just calculated. Or you can write in simple term, uh, your absorber area is, okay, sorry for this, so your absorber area is this heliostat area, right, this is your actual, your sorry, your basically aperture area, right, these are the aperture area. So it will be number of heliostat into area of each heliostat. This will be the your aperture area, and your receiver area you have just calculated the AP value, which is your 189.66, right. So you know the number of heliostat, it was 1800, okay, and your area of each mirror was 6.5 into 6.5 divided by 189.66. So if you solve this, your concentration ratio will come to be 404 point, this is 0.07, or say 404. Okay, so this will be your concentration ratio. So the size of the image that we have calculated is 7.952. So 7.921. So it's this value. Size of the receiver that we have calculated is 189.66. So let's see. So it's similar to this value, and concentration ratio was 404. Okay, so this is how question will be framed on solar tower. So I hope that this session was helpful to you, because I have included all the questions from how it will be framed from solar tower, how will be based on solar parabolic trough collector, all this even simple numerical problems about the system efficiency and concentration ratio for linear um, basically collectors. So any doubt in this, any of these questions? Okay, so again, if you have any doubt, you can always come back to me and ask the question in another session, or raise your question on the SWAM portal. So I will end this session now. Hope this session was helpful to you. will be helpful to you in solving the assignment question and for a final exam. So thank you all for listening. I will end this session now. Okay. So.